Most people think submarines sink by filling up with water, like pulling a drain in reverse, and that's part of it. But that's the easy part. The real question is, how does a 7,000-ton steel tube hover perfectly still at 300 meters underwater without sinking to the bottom or rocketing to the surface? Because getting that wrong doesn't just mean a bad day, it means losing the whole boat. That's exactly what happened in 1963, and we're going to get to that. But first, we need to understand the physics that makes any of this possible at all.
Let's start with something a Greek mathematician figured out over 2,000 years ago. His name was Archimedes, and his idea is still the reason submarines work today. Here's the simple version. When you put something in water, the water pushes back. If the thing weighs less than the water it pushes out of the way, it floats. If it weighs more, it sinks. That's it. That's the whole rule. So the challenge for engineers was this. How do you build a steel ship that can switch between floating and sinking and then stop exactly in the middle? Think of it like a balloon. Fill it with air and it floats up. Fill it with rocks and it drops. But fill it with just the right amount of water and it hovers right in the middle. Not floating, not sinking, just hanging there like a ghost. That middle state is called neutral buoyancy. And that is exactly what a submarine has to hit every single time it dives. Now, the first submarines to really solve this problem were the German Type 7 U-boats from World War II. These were the submarines you've seen in old war movies. Long, dark, built for hunting ships in the Atlantic Ocean. The Type 7 had a clever design. It had two hulls, one inside the other. The inside hull, called the pressure hull, was the strong steel tube where the crew lived and worked. The outside hull was lighter, and in the space between them sat the main ballast tanks, or MBTs. Here's how a dive worked. At the top of those main ballast tanks were vent valves. Open them, and air rushed out. As the air escaped, seawater flooded in through holes at the bottom. The tanks got heavier, the submarine got heavier, and it started going down. Think of it like an upside-down cup in a bathtub. As long as there's air trapped inside, the cup stays up. But poke a hole in the top and the air bubbles out, water rushes in, and the cup sinks straight to the bottom. To bring it back up, you'd have to blow through a straw into the cup to push all that water back out. That straw is exactly what the high-pressure air system does inside a main ballast tank. But here's the part that surprises most people. Flooding those tanks doesn't stop the submarine at a specific depth, it just starts the fall. Something else entirely has to stop it and hold it there, and getting that wrong means the submarine either bobs right back to the surface, or it keeps sinking until the pressure outside crushes the hull completely flat.
So the Type 7 solved the basic problem, sink or float. But modern submarines had to solve something much harder. They had to do it precisely, silently, and at depths that would crush that old World War II hull like an empty soda can. The modern benchmark for this is the Virginia-class nuclear attack submarine. Single pressure hull, pump jet propulsion, built to go places the Type 7 could never survive. The Virginia class uses two separate systems working together to control depth. The first is the main ballast tanks, same basic idea as the Type 7. Flood them to go down, blast compressed air in to come back up. But these only get the submarine close. They handle the big, coarse adjustments. The second system is the trim tanks. These are much smaller tanks inside the submarine. They shift water forward and backward, like moving weight around a canoe to stop it from tipping. They handle the fine work, leveling the boat, adjusting the angle, keeping everything steady. But here's the part that nobody tells you about. Even with both tank systems working perfectly, a modern submarine isn't just floating at depth. It's actively flying through the water. On the bow and stern of every attack submarine are movable fins called hydroplanes. These work exactly like the wings on an airplane, except they're pushing through water instead of air. You've probably felt this yourself without realizing it. Put your hand out the window of a moving car. Tilt your palm up, and the wind pushes your hand up. Tilt it down, and your hand gets pushed down. That's exactly how hydroplanes work. Angle them down, and forward motion pushes the nose of the submarine deeper. Angle them up, and the submarine climbs. Depth is driven by movement, not just by how heavy the boat is. And that detail matters enormously, as we'll see in a moment. If you're the kind of person who loves understanding how big machines actually work from the inside out, hit subscribe.
We break down one mechanism every week. Now, all of this has to happen inside a hull that is fighting off something almost impossible to imagine. At 300 meters deep, the ocean is pushing on the outside of that hull with roughly 30 times the pressure of normal air. Every single square inch of the hull has the weight of a small car pressing against it. Think about being at the bottom of a giant human pyramid with 100 people stacked on your shoulders. That's what the ocean is doing to the submarine, on every inch, all at once. And it gets stranger. When a submarine dives deep, the water squeezes it so hard, the whole hull actually gets a tiny bit smaller. Just like when you suck all the juice out of a juice box and the sides cave in slightly. The hull is engineered specifically to resist that squeeze without cracking or collapsing. The material that makes this possible is called high-yield steel, specifically grades known as HY80 and HY100. Those numbers refer to thousands of pounds per square inch of force the steel can handle before it permanently bends. Around the inside of the hull, ring stiffeners run like ribs, spreading that compressive force evenly so no single point gets crushed first. The circular shape of the hull isn't a design choice for looks. It's the only shape that distributes pressure evenly all the way around. Any flat surface or sharp corner becomes a weak point. A circle has none. And the way the submarine moves through water, quietly, comes down to the pump jet propulsion system. Traditional propellers create tiny bubbles when they spin fast enough, and those bubbles collapse with a sharp cracking noise called cavitation. The pump jet eliminates that. The machinery inside is also mounted on vibration-isolated platforms that physically disconnect the engines from the hull, so the mechanical sound has nowhere to travel. The result is a 7,000-ton machine that can move through the ocean almost silently, holding precise depth, fighting off pressures that would destroy almost anything else humans have ever built. All of that engineering, the main ballast tanks, the trim tanks, the hydroplanes, the high-yield steel hull, it all has to work together, every time without fail. Because at 300 meters underwater, there is no margin for error. On April 10, 1963, the USS Thresher left port for a routine deep dive test off the coast of New England. It was the most advanced attack submarine ever built. The crew aboard numbered 129 men. What likely happened next has been pieced together from the evidence recovered and the last transmissions picked up by a nearby ship. A pipe fitting in the seawater cooling system failed under pressure. Water sprayed into the engine room. The reactor, sensing something wrong, automatically shut itself down. In an instant, the most powerful machine on the submarine went silent. No propulsion, no forward motion. And remember what we said about hydroplanes. They only work when the submarine is moving. Without movement, those fins were useless. The submarine had no way to drive itself back toward the surface. The crew attempted an emergency blow, blasting high-pressure air into the main ballast tanks to force the water out and push the boat upward. But the rapidly expanding air cooled the valves so fast that moisture inside the lines may have frozen solid, blocking the airflow before the tanks could clear. The submarine was sinking. The systems designed to stop that were not responding fast enough. The Navy picked up a garbled transmission from Thresher, then silence. It took weeks to find the wreckage, scattered across the ocean floor in pieces. All 129 men were lost. In the aftermath, the U.S. Navy launched the Subsafe program, which stands for Submarine Safety. It was a complete redesign of how submarines are built and tested. Brazed pipe joints were replaced with welded connections. Emergency blow systems were redesigned to prevent icing. Redundant backups were added to every critical system throughout the boat. Every Subsafe certified submarine built since has never been lost. Not one. That is the direct line from Thresher to every modern submarine in the water today. Every valve, every weld, every backup system exists because engineers sat down and calculated exactly what happens when something fails at depth. A submarine hovering silently at 300 meters is not passively floating. It is actively balancing main ballast tanks, trim tanks, and hydroplanes inside a hull built to survive pressures that would destroy almost anything else. None of it is magic. It is physics, pressure, and hard-learned engineering.
The next time you see a submarine on the surface, remember, that is the easy part. If you want more breakdowns like this one, subscribe and we will see you in the next one.